joking. In fact, I guess.
Okay, so the first thing I wanted to do, though, was just one more thing on that 1D conservation of mass, where we had talked about just because we have a special, so dsdt equals, well, you put it this way, dq ds ds dx. Oops, that's not right. It's not. And then this, if this is a constant, then this ends up being the speed of a kinematic wave that travels down. So our s at some later time is equal, looks just like the s at the initial time, but translated down. So time, for our initial function of s, in this case I'm going to make it a nice curve instead of the weird one. So this is at S0. Wait, this is with position x. So this is our one dimension in space, and this is our amount of stuff. And at time S2 or S1, some later time, what this solution, this simple solution basically just says is that it gets translated down at some speed c. So this is our S1 at time t1. And this purely comes out of conservation of mass. You don't have to bring in any fancy fluid dynamics and get into crazier equations, which you'll get into in other ways. But there's a lot. This is just, I think, one of the ways that conservation of mass ends up being a pretty powerful way to get at solutions to problems. And for this all depends on there being this relationship between the flux and the amount of stuff. So more stuff means higher flux. And that's the most common or very common way that we interact with this when the flow of stuff is related to the amount of stuff is rivers, where the thickness or the amount of water in the river determines how fast it ends up flowing, all other things being equal. So for a river, you often get, and we'll actually derive this probably on Thursday.
I want to say that actually the more stuff, the faster, because basically there's an increasing gradient between more stuff and less stuff. Is that a fair way to look at it?
Yes, because, well, when we get into rivers, yes, it's the slope of the river, but it's also the thickness. It's the slope and the change in thickness from one point to the other. Because a swimming pool has a flat surface, so you put more stuff in a swimming pool, it's not going to go anywhere.
Well, but if I put more stuff in one place and not the other place,
right,
I do create a gradient.
Yes, so you do create a gradient, and yeah, we'll get to. So yeah, it is more the difference in stuff ultimately for rivers that ends up driving a lot of it. But we can simplify that by just knowing that more stuff equals higher flux in these cases, and we can derive that relationship. You derive that relationship from the conservation of momentum, but once we kind of know what that relationship is, and in this case for rivers, it's that the flux is proportional to the cube of the amount of water, and that's something that we can derive from the conservation of momentum. But if we already kind of know that relationship, then we can do a lot with the conservation of mass. In this case, so then if Q is the cube of S, then dq ds is equal to 3s squared, which we'll see when we get into the conservation of momentum, means that this is 3 times the velocity of the water, because the velocity of the water is a function of s squared. And so, yes, these details do come out of a conservation momentum, but you can get pretty darn close. I mean, once you know this, which is kind of a general way that water works, we can then use this conservation of mass to really start to look at what's happening in this environment. And what I wanted to do was take this idea that water, or that the flood wave, so this bump, if it's a flood in a river, this bump should be moving at 3 times the speed of the water itself. So this is that information traveling faster than the actual molecules are moving. And what I wanted to see if we could do, and this is hot off the press, if you guys have been listening to the news this week, there's a big flood happening in Iowa right now. The Cedar River goes through Cedar Rapids, Iowa. And I found a bunch of hydrographs from USGS stations along, this is the Cedar River watershed. I can pass these around. The rainfall all happened up here in this Floyd and Butler counties. So this is where they had something like 12 inches of rainfall last week. On the 22nd, I think it all started. And then the river flows down here, and they've been having flooding problems now all the way down. So even though it didn't rain down in this lower part, they're having major, major floods. And this was just a little news report where it said totals have exceeded 12 inches in isolated spots within Butler and Floyd counties. And this was written last week on the 22nd. So what happens when something like that happens, basically the hydrologists at the USGS go into power prediction mode where they're like, okay, there was all this rainfall. What is that going to do downstream in terms of the flood? What are the exact dates and times they can predict the flood stage will be on the river lower down? And they do all of that pretty much based on this concept, not any crazy dynamic modeling of the river itself. It's just knowing the river system, and that we have to conserve all of that mass. And then they can see what's happening on all of their stations. And so I think these are going to be in order. So what we're going to do is look, these are what are called flood hydrographs. This is a good example of one. Some of them are better than others. So this one is at 1 p.m. on Wednesday, September 21st. There was nothing in that river. Within 24 hours, that river went from being at a level of 6 feet to 21, almost 22 feet.
Oh, dang.
Within 24 hours. And that's this part of the curve. So that's at one location where it went, and then it slowly dissipated back down as the flood went. So this flood, this is the front. This is at one location. Basically, it's like here, and this was time one was all this rain lumped on top, and this station was here. 24 hours later, it was up here. We didn't put a tail end on this, but obviously, if the rainfall stops, there's going to be a tail end on this. It's gonna go back down at one point, and so it goes up and then it goes back down, and that's what a flood hydrograph just tells you at that one point through time. How does that change? And so by looking at a bunch of stations along the river, you can actually estimate the movement of this flood wave. And so I printed out a bunch of these, and I think they're sort of in order of locations. So there's, and I don't know if you can, one of you can look on there. We might have to look on a map to make sure we get the right locations. But this is at Lansing and then at Austin, which I think are more above the flood. And then this is Ontario, St. Ansgar. Are any of these showing up on there?
Mm-mm.
I know some of them. Well, this one got kind of cut off. I'm not sure why. And we can bring up a map of the area. Oh, good. There's one that's not even on. That's useful. Nothing there. Charles City.
It's a negative.
And then Waverly.
Did you say Cedar Falls at one time?
Cedar Falls will come up here. I think it's down. Yeah, this is the Cedar Falls one. It's right there.
Oh, there's that.
And then, and these just have some extra prediction information with them. This is at Waterloo.
Yeah, let's see that.
It's moving down the river.
Mm-hmm.
Where are we at?
Right here.
And
Okay.
Vinton.
That's not down here.
And so what I want you guys to do is kind of pick off dates and times. We'll pull up a map to look at what's where and see if we can translate it on there and see how fast this flood is moving down the river. Here's Cedar Rapids.
Oh, I see that, yeah.
It's your favorite spot, huh?
And Conesville.
I'm just gonna guess that we're in order.
And Cedar Bluff is the last one.
It's good math. Mm-hmm. Doesn't have cities or anything like that on it. Looks like just counties.
So I'll bring up a map of the whole thing, but just with your pencil, go in there and see if you can pick off on any of those, the beginning, the upsweep, and then the peaks. And we'll create a little analysis. And those, some of those didn't have, but I think those are actually more upstream.
Those are like two peaks.
Saturday, 12 p.m. Saturday, 12:30 p.m.
That's at 12 p.m. That's 12 p.m. That's it. Let's do that.
6. That's up here. It's at 6.
Yes.
P 24.
Where is that?
Tuesday, 12 p.m.
If these have like two peaks, do we go with the first little
That's way
up
lower.
up shot?
I don't know. I'll see what
Oh, that is. I would probably say the
The first one would be
maybe the
when it first
peak is 'cause,
increased.
like,
probably the first.
if there's some noise in like where the rain is coming from, the big wave will. I mean, it will actually. It would affect when the like overall peak is.
Okay, so
Thursday.
Interesting. It takes a long time from when it starts to when it really builds up, but I guess that. This one
what's
starts
this Austin one?
Thursday.
1 p.m.
Oh, you're doing the
How do these come after the
This would be. There's that. 1, 2, or about 2 or 3 p.m. and it's all 3 p.m. Saturday.
So which one? This one is Ontario.
I
Toronto?
see a difference here.
Yeah, I don't think that's.
One
This one sort of peaks at Thursday.
It's not. It's
At 6-ish.
OTRANTO.
Yeah.
Oh,
A little after 6.
OTRANTO.
7.
Toronto.
There.
10. I don't
Wait,
know.
sorry, this one?
This one. Yeah. Because are we looking at this peak
Oh,
or are we
s-
going to look at this one?
Okay, so they are.
Said probably
That
go to
might-
the first one.
Yeah, this could be if there was localized rainfall in between
Yeah.
this station and that station, and that
Yeah.
would probably be the second peak.
That's why we were going with this one. Well, this could be
Actually, it would
localized
probably
rainfall,
be. I would say
couldn't
the lower peak would be if it was
it?
localized
That's what I'm saying.
rainfall.
This could be localized rainfall.
And then the
Oh,
highest
yeah, I
peak would
already-
be.
Because the rest of these,
I
the
mean, I
peaks
said
are
at
around
start,
the
but
same
start
day.
is
Yeah.
not
So the rest of
necessarily
these, all these peaks
so,
are on Saturday or Sunday or whatever, and this one would be
peak
the
is
only one
Monday
that's
at
on like
6
Thursday.
a.m.
Thursday noon.
So I think if we went with this peak, then it's like 6-ish, 6 p.m. Saturday. This one kind of has 2 peaks. Yeah, but see, this peak is on Friday. If it's lower down the river, it should have come after that. So that's why it led me to believe which one of these to use, because this one's higher up than this one. What are the rest of those days?
The 22nd is the peak.
So Thursday?
Yeah.
So then this
Yeah,
one, it'd be
this is-
Thursday. And
yeah.
then this is Friday. This goes
This
to like
is Saturday about
So
noon.
I guess we'd use this first one.
Waterloo is then Monday at 6 a.m. Or wait, no, that's Vinton. Sorry, Waterloo is Saturday at 3 p.m. Waterloo, the peak is Monday at 6 a.m.
Wait, so you said this was, what is,
Waterloo
So,
is
okay,
3
Saturday.
p.m. Saturday, 3 p.m. So actually, Cedar Falls and Waterloo must be fairly close on that map.
yeah,
Oh,
they're right
Yeah,
here.
it's actually.
The Cedar Falls and Waterloo are actually pretty close, so that makes sense. I don't think any of the other names really showed up. Where's
Cedar Falls is right above Waterloo.
Yeah, they're right beside each other
Okay.
on this map at least. Cedar Rapids is a bit further down.
Yeah, Cedar Falls, and it took about 3 hours for the peak to travel from Cedar Falls to Waterloo.
So that's 3 hours.
Um,
And what about the beginning?
well, yeah,
These upsweeps
Sort of.
are kind of cut off here.
yeah, some of them it's
This
kind of cut
upsweep.
out.
What about between Cedar Falls and
So, I mean, you could just go by
this
this
upsweep comes around Thursday.
start, I guess you could say, right, like here or something. So the start would be Thursday at 1 p.m. and then Thursday at, I mean, I guess you could say
I found
Thursday at about 4 p.m.
We have St.
Yeah, the-
Ansgar.
3 hours.
It's a little down. I'll have to zoom in eventually.
These are pretty much identical. I feel like they're probably very close. 'Cause
Yeah.
The upsweep's the same, or 3 hours.
Like I would say
About.
The upsweep is also 3 hours.
Yeah, about, I mean, it's kind of tough to, like, estimate, you know, where,
Some of it looks kind of cut off on some of these,
you know,
but
Yeah.
where on this do you think the starts?
or does it start to upsweep?
I just said right here. You could say here, but I just said there.
Well, on
Flat
some of them
for a
it's just
while.
cut off. It looks like it's about that point.
Oh, right.
So,
So between
And then my
that
other
and
question
here
is,
was
how
75
long does
hours.
it take from the beginning of the upsweep to the peak?
Oh.
Um,
I'd say between these
so
is
the
like 2
difference
hours.
here
2 hours.
is
This is
in
3 p.m.
Yeah.
on the other days.
Yeah.
Thursday.
You said this was about 1 p.m. to about. What do you have for Cedar
Okay,
Falls?
Cedar Falls, Thursday 1 p.m. to Saturday 12 p.m.
Okay.
Again, 47
So this one, you can't really see the
hours.
upsweep.
it's like
I'm gonna
36
guess-
hours from onset to
I'm
peak.
gonna guess Wednesday. The upsweep here
And what's your date and
Yeah,
time on
the-
with the
to
Otranto and Cedar
Friday at
Falls?
6.
What's the time?
There's
No.
Cedar Falls.
Uh,
Here.
What day is What's your onset for Cedar Falls?
36,
We
42.
a little cut off, but Thursday 1 p.m.
What's
is
the
when
date
it
of
started.
Thursday?
Oh, it's the
22nd.
22nd.
1 p.m.
Yeah, about probably a little before that.
About
Actually,
Cedar Falls
42,
to
but
Cedar
this might be.
What was peak?
But if this upswing starts back
Friday
here, that would
23rd
change it.
at
Yeah, but
These
we
two
can't see them.
noon.
Sorry,
12
what
p.m.
the upswing time?
Yeah, I'm curious. She got 36 hours for the upswing.
In the
From the
Cedar
beginning.
Falls and Waterloo, it's about 47.
47.
It's 47
47.
exactly at both.
Okay, and then what's going on down between Cedar Falls and Cedar Rapids with that?
How long does it take between the
The-
swing and the peak?
The Vinton one, it takes 42 hours. But
Although
the
that
tail
one-
is kind of cut off. So
Yeah,
you
or the
can't
beginning
see
of it is a
the
little bit
start.
cut off, and so it could be more
Oh, I
like
see.
45. We can't be
Okay.
Kind of hard to
certain.
tell.
Then this one's really long. It's 75 hours.
75 hours. So 45 was Vinton,
Yes.
and 75 hours was which one?
Is Palo. Halo. Whatever.
Find that. 75
Yeah, well,
hours was Palo.
I would mark the start of this like
And
over
then
here.
what do you have for
From Otranto to Cedar Falls
Personally.
was 38
Oh.
hours.
3
I mean, does that?
hours?
I don't know. I guess it depends. I had been marking some of these like right when it starts getting really steep.
But this one never gets
And then
really
Cedar
steep.
Falls to Cedar
Yeah,
Rapids.
I mean, I
what's
guess
the,
it's steeper.
the time
there.
difference?
It just a different
Cedar
way to-
Falls with Cedar Rapids.
Cedar River at Cedar Rapids, I got an approximately 66-hour difference between the start and peak.
Are we saying between the
So
start of Cedar Falls?
Rapids is 66 hours for the sweep up.
Yes.
Okay. And then what about the time from traveling from Cedar Falls to Cedar Rapids?
Are we looking for the peak?
Oh, what time?
So this
is-
was-
I did
12 p.m.
onset
Friday.
for
You did onset.
Toronto,
Cedar
yeah.
That's the
Rapids
onset
starts at
then.
6 p.m. on
For here,
Saturday.
it's 1 p.m. Thursday.
And what is it
6
at?
p.m.
Cedar?
Saturday in Cedar. Oh, let's see.
This is 1 p.m. Thursday on Cedar Falls for the onset. She was asking what the onset is. What's Rapids onset?
6 p.m. on Saturday. That's when it starts.
My time's not working with me in my head.
is,
Can't work on 24-hour scale.
48.
It's not
1
these
p.m.
10.
Well, and the fact that these are
Uh,
like the dash marks are at 1 p.m.
Okay.
I understand that's when they take the measurement, but like, just move it an hour.
Yeah, that's what I was looking.
47. Or, I mean, sorry, not 46. No.
53.
53 hours.
53 between their
And then
onsets.
the peak. What time is the peak at in Cedar Falls?
12 p.m. Tuesday. This is Cedar Rapids.
Or, yeah.
In Cedar Falls,
Too much
it's
Cedar.
12 p.m. on Friday. That should be easy.
Sorry, what did. That was 12 p.m. on.
Tuesday.
Al, do you want to write some of this down on the maps? I'm afraid it's going to disappear on this.
Sure.
Okay, so.
12 p.m.
Oh, that's.
Friday here.
12 p.m.
Actually, I was wondering
Saturday.
if you
My
move
bad,
your
12
map,
p.m.
the
Saturday.
Google Maps is
I just
the
noticed
marks
that.
move. Was it? Probably not,
Sunday,
right?
Monday, Tuesday. Okay, 72 hours.
Maybe you should try.
Between their peaks.
Yeah.
I think right now I'm in drawing mode, which it fixes the.
You can print screen the.
Oh yeah, you could print screen. That's
Oh,
true.
that's fine. Is it control?
Shift 4. Command Shift 4.
Oh,
Command shift.
it's one of those controller command. Oh,
6 hour
okay.
difference.
3 is the one that's the whole
From-
page, the whole
Vinton,
screen.
Cedar Rapids.
I didn't know if you wanted.
Oh,
Are you looking
we
for
don't.
a-
Yeah, the Vinton.
I have to
I don't
Google
know
that
where
every
Vinton
time.
is on the map.
I always just test between control and command because I forget which one it
I'm
is.
guessing. I would guess Vinton is closer then. Also, the start of it is maybe a little bit cut off, so.
So yeah, if
9 a.m. Sure, 9 a.m. or something.
so at the beginning, it takes 36 hours to go from the initial to the peak, right? And then 47 hours at Cedar Falls.
66 at the.
66 at Cedar Rapids, and 45 was at Vinton. That must be somewhere a little closer to Cedar Falls, I'm guessing.
I would guess it's closer to Cedar Rapids. The start and end times of Vinton are more closely related to Cedar Rapids, I mean.
Cedar Rapids. Okay, and then it takes 75 hours down at this Palo. What is that? What do you think that's evidence of? Our little S curve is not.
It's diffusing.
Yeah, so this is where it's diffusing a little bit. So we're getting, like, it's moving down, but it's also decreasing in its magnitude. Okay, so we got that down. Now let's figure out what these distances are. So I'm gonna have to go away from this, which is, I did take a screenshot of this, but if you can.
Yeah, I'm trying to find the places in the map.
So
Yeah, 'cause they're not on this map.
Otranto is near this border, near Austin, in the upper area.
I mean, it really doesn't even have cities like Austin. It's more of a county
Okay.
map.
Well, we'll figure it out. So Otranto to Cedar Falls was 38 hours, and then Cedar Falls to Cedar Rapids was 53 hours. So those are the two key. And then we could look in detail if we wanted to. There's a 3-hour one there and a 2-hour one there. But let's take these big ones. So 38 hours and then 53 hours. I think. So if we go Otranto to Cedar Falls, it's 87.6 miles.
But that's not. The
That's
river
on the
doesn't.
road,
Yeah, the river
right,
does
that's
not
Yeah.
follow the road.
That's a road, not a river.
You can open Google Earth and then put little drop
Draw.
points.
Yeah.
That's what we should do. I've never been to Iowa.
Isn't Hillary from Iowa?
I've been through
It's
Iowa
more
for a
pleasant
while.
to drive through than Illinois.
It's true.
And
Illinois is a
everything's
bit
nicer
boring.
to drive through than
Or,
Nebraska.
Or Nebraska, so.
Nebraska's the worst.
Nebraska, yes.
The Illinois is so flat,
Just
and I lived there
fields.
for 8 years, so I know the moment you get into Iowa, there's a giant hill you go down and up.
Yeah, I used to drive from North Dakota to Colorado and going through Nebraska and Kansas one after the other. It's just like
Yeah.
The world's
Gonna
largest
murder
truck
someone now.
stop is on I-80 in Iowa. So the sign claims.
I think this is that little. Oh, no, that's Charles City. So there's St. Ansgar. So there's our Otranto. St. Ansgar, Osage, Charles City, Nashua, Waverly, and there's Cedar Falls.
And Waterloo, they are right beside each
And
other.
Waterloo right next to it. So Cedar Falls is right there. Okay, so from here to here in a straight line
Which is close to a river.
is 120 kilometers.
Yeah.
So you can calculate the kilometers per hour there. And then from Cedar Falls to Cedar Rapids. It's only 90 kilometers. That's a really crooked river there.
You can add a few more kilometers to.
Yeah, it actually looks straighter between those two. It's quite,
Call it an even 100.
so at least, yeah.
So 100 kilometers, roughly.
So, but it took 53 hours for it to go there. And
53 to go where?
53, I think, to go from
Cedar.
Cedar Falls to Cedar Rapids. But only 36 to go from Otranto to Waterloo. And one thing.
So it's almost 2 kilometers an
Let's
hour
see.
from
Yeah.
Cedar Falls to Cedar Rapids.
It's 3.1 for the top part.
Actually, that's probably fairly.
Do any of those have the river speed on them, or they have the flow? Volume flow.
Yeah.
Just flow.
Cubic feet per second.
Yeah.
Mm-hmm.
Here's the stream velocity at Waverly.
Better than cubic forlongs before.
So you can see as well that it, in this is just the velocity, not the stage. But it also increased in velocity. But it's moving at 3 feet per second at its peak speed. So whoever's good with units, how long would it take it to go at this speed? The
So, a
physical
meter per
molecule of
second.
water, it's going 3 feet per second, and it has to go how many kilometers? 100 kilometers?
100 kilometers.
2
That's a meter
kilometers
per
an hour.
second. So that's why 3.6 kilometers per hour.
3 feet per second is, it's actually a pretty typical speed for a decently flowing river. So it's,
Yeah.
can you imagine walking 3 feet per second? It's a little bit faster than walking pace.
That's like the
Yes.
same velocity we
'Cause-
got for the top portion of the river.
It is,
Yeah.
the
Feet?
flood,
Pretty close.
the
But
flood
No,
speed and
converted to
Oh,
kilometers
okay.
per hour.
It's like 3.4-ish
Yeah,
kilometers per
3
hour.
point,
kilometers
3
per hour, and that's how fast the flood went as well.
3.17 was what we got for the flood.
Surprised it's not moving much faster. But,
These are
It
really
is-
rough
wait, that-
estimates
they're rough
too.
estimates, and the base flow of the river is only goes at 1 foot per second, so it did. But that 3 times the velocity is actually, doesn't account for side drag, so that's actually on the high estimate. And again, then there's the base flow versus, cause it doesn't start moving at this speed until the flood's already arrived. So it is moving almost 3 times faster than the base flow. It's just not moving 3 times faster than the peak flow once the flood has already arrived. So I think that it would make more sense to look at it. And also, this is just a 1 point velocity. It's not an average for the full river. We could look up other ones. But does that give you a little bit of a sense for how this works? I don't know why there's that double bump. There must be some,
Localized.
there might be, I can think of
There's a fork of
one.
two. At
Yeah.
the confluence, you have a delay between two.
So it's happened
Yeah, exactly.
because it was here, very pronounced. Then there's still a slight little hump here,
Where
and
does
then
it
it
start?
completely goes away.
So
single.
yeah, so if you have two
So 2 locations
tributaries
though.
that are both being rained on,
One has a longer path than the other.
right, so they get the rain at the same time, but they don't follow exactly the same route, and they may not have exactly the same, but they're pretty
Yeah.
close. If it's a little bit of a longer, then when they converge, you'll be merging the 2 hydrographs. But then the diffusion effects will kind of smooth out the bumps as you go further downstream. So, cool. Any questions?
How about the rain records? Like which area in Iowa the rain hit?
Where was it?
Yeah, where was
It was around. I don't. Where's that map? The Otranto. So the Otranto is really the upper part of where it flooded.
It's above Mason City, I think, isn't it?
Is that what that's what the.
That's what your other map
said.
where you drawn some stuff. I thought it was above
Yeah,
Mason City.
I think it is kind of near Mason. I wasn't able to find just a simple map of where it was.
Yeah, this looks like Charles City, maybe?
Oh, well, Charles City is definitely below.
Yeah, that doesn't seem...
So they said Floyd and Butler counties, which go from here to below this one, a couple more below Mason City area. But, I mean, that was, yeah, I mean, it kind of said that it was mostly up here. And that's as much detail as I could find. I couldn't find just a map of precipitation, total precipitation as a function of distance. Although that might be what, in the background here,
Yeah, but
that bullseye.
Charles City is like down...
It's
Here.
below Otranto.
Yeah,
Oh,
Toronto's
you're
like
right.
way up
Toronto
here.
is the way this is set up, yeah. Because Charles City is here?
I think it's further down.
It's not below Cedar.
It's like right in
Oh,
here.
there's Waterloo.
Yeah, because you thought at first you
Yeah,
thought it
there's
could have
some-
been Cedar Falls or whatever when you zoomed in on the map.
Yeah. Yeah, I think you're right. And that's kind of at the base of this. So, but obviously it was raining also all the way up here.
Yeah, here's Charles City. So it's like...
So that's the end of it.
Oh wait, but this is...
That's it. For some reason, some of them didn't.
They all started at Thursday.
A bunch of them started on
Oh.
Saturday.
How symmetric
Oh,
are they?
okay.
Yeah. So these are, I don't know why.
So it cut off the Thursday
Yeah,
stuff.
cut off the beginning.
Which
So we
is
just
the-
see the ends of it
Yeah,
here.
which at the top would have definitely been in
and this
Thursday.
is the
and-
first one that starts on. This one actually started on Monday.
Yeah.
So I don't know why they
So
chose
I
that.
actually probably would be interesting to look at the forward half max of the peak, then you can get the diffusion rate probably. But
Yeah, I mean, if we were to do like a little GIS and do a layer of the precipitation totals and a layer of the peaks, and you could visualize it all the way down, that would be cool. So yeah. And it hasn't even hit down. What's the end spot there?
Cedar Rapids near Conesville. Or is that Cedar?
Cedar Bluff.
Do we have an Iowa City all the way down there? Or lower? Because that very last one, it looked like it hadn't even hit it yet, right?
This one, the Cedar Bluff one, the peak is kind of cut off.
And that's right now. So the
Yeah,
the
this
peak
is...
hasn't happened yet. And they don't have the prediction on that one, I guess. Cool. Anyway, I thought that was interesting news.
Pretty neat.
Yeah.
I noticed that there are some of lakes in the track between the 2 points, so some of the water might go to lakes. Like concentration of masses, I don't know,
Yeah.
it's hard to calculate.
It's a really good point. You would definitely, if you wanted to do all of this in detail, you would have to
Consider a little
consider
like minor.
both tributaries coming
Yeah.
in, the lakes that might pool and provide they might just slow down the process because they're kind of buffering the volume discharge.
Nothing's ever as nice as your model that you use in classes, is it?
But a lot of the best science ideas come out of sticking with a pretty simple model. And so you can still publish amazing new conceptual stuff with a simple model. And so even though you guys, and I thought this too when I was learning all this stuff, that everybody's already done all the simple stuff, and so the rest of the science is all going to require complex, three-dimensional, fluid dynamic flow for us to really learn anything more. And turns out it's really not true. Like every time I turn around, I'm like, well, why didn't somebody think of doing that before? And so
You have a lot of measurements, so that's
yeah, whether it's because there's new measurements that come out or just because you're looking at it from a different perspective than everybody else, you can still write papers that are primarily based on one simple equation and show something pretty powerful. So even though some of our equations are simplified examples we do in class seem very simplified, it's actually good to look for that simple version in your research too, because it's often there. And if you always go straight to the complex, you're gonna miss a lot of cool things.
Yeah, I'm always taken back to one of the problems we did in my physics class where at the end of the problem, it was something to do with a cow and dropping it from a plane or something. It's like, assume a spherical cow. I'm like, that's what we live in. That's the world we live in physics, is spherical cows.
I always assume a spherical physics student in a vacuum.
Yeah.
So the problem that's in your homework based on this is snow falling on a glacier, because I'm a glaciologist, sorry. I think I realized that I gave you guys like 3 different glacier problems on this, but they really are the same concepts. Snow falling on a glacier, which like a river, it has to then move with the ice downslope, and in the glacier's case then it melts or disappears at the end, and so you can look at, similarly you can get a lot out of how a glacier behaves from just looking at mass balance. I'm actually writing a paper right now that does all of the glaciology as simple mass balance. Mass in has to equal mass out, and I've come up with velocities. I've got all sorts of results from it that look like I had to go to a ice dynamic model, but I didn't. So when you do need to go to the crazy dynamic movement of the system, then we go into the conservation of momentum, which actually, do you guys want a quick break? Yeah. Okay, 3-minute break.
Good deal.
Although we've been moving around a lot.
Yeah.
Aaron, what is this little piece of paper for?
That's the topic for your problem design. What does yours say?
Okay.
So
Problem.
the
is
problem design is
October 23rd.
Yeah, so it's in place of like a typical midterm exam. You have to write your own exam problem.
Like in class, right? We have to write it in class.
No, you write it at home.
Oh, I see.
You write it at home and then you submit it, so you can think about it and work on it between.
So you solve it also at home.
Yep, you solve
Okay.
it also at home.
So there is no like midterm, like typical undergrad
No,
class.
there's not a normal midterm.
Okay.
You write your own midterm problem and then.
Because I remember,
you solve
I
it.
think I misheard that. Like we'll be here in the class, and then you will give us like some topics, and we have to write it in 2 hours. Like, is that?
Maybe the
No.
finals in the 2
The
hours.
final is 4 hours.
Oh, that's the final.
But,
Okay.
And it's not in class. It's supposed to be.
it's the final you check out from Blackboard and it starts the timer and then you have to resubmit it 4 hours later. And we do that because, does anybody going to AGU? 2 people are. So we do that, we give you a little bit of flexibility with the final because of AGU always complicates things.
Yeah. That's what I was warned by some of the former students. Like, oh, if you're going to AGU, you better prepare ahead of time and don't wait till the last minute to do things because
Yeah.
AGU
we
will
try
be
to-
busy week.
We try to make it work for whoever's going. We try to kind of,
Which there's time in between talks and stuff at AGU to do things. I mean,
there
Yeah,
are.
I mean, you're
and
not gonna
I
want to
would
do
recommend either
stuff.
doing it before, and this is what we'll
Oh,
kind of
yeah.
talk. We need to look at the dates, and Jeff will talk about this. But either trying to do it like the day before you leave for AGU, or depending on where the final. I can't remember where AGU sits in our final exam schedule. We usually encourage people to either do it right before they leave for AGU or like the day they get back from
Yeah.
AGU.
that's my plan.
And
For the questions, are we expected to use MATLAB to solve stuff, or not at
No,
all?
it's
Actually.
supposed to be like like you're making this for somebody who's gonna come in and take a test.
Okay.
So it's supposed to be straightforward enough that they can do it sitting down in
So we
somebody
can model
who's
it
studied
after
well.
we can model it after one of your problems, right? Like,
Yeah, but
like
Yeah.
the
But the
idea,
but the
like you have
homework
points.
Yeah, the homework problems that I've given you so far, the main difference is that those are a little bit longer.
Yeah.
And so imagine that style of problem,
Yeah.
but one that's written such that somebody who really studied well and could do it in a half an hour to 45 minutes. So you give them the pieces that they need. Any calculations, if you actually want to put numbers in there, they should be simple enough that the student could do it there with either just in their head or.
Yeah, are we
very
allowed to use a
simple
calculator?
I think I'd rather, if it is just the simplest, but I'd rather you actually, I think it's easier if you just give them simple enough numbers, divide
Okay.
by 10 or something kind of thing. If you really want to put something in that requires a number,
Oh,
that's
I thought
fine.
this was for the final.
The final will be problems like this where.
Okay. Yeah.
where
You'll take the questions you accumulated over the.
So-
we do look. The
So
ones
on the
that-
final, are we allowed to use a calculator?
I think a simple calculator, but not MATLAB.
Okay.
I can't remember what we said, but we don't give you that many that actually require numbers.
I have a slide rule app on my phone. Am I allowed to use that?
Nope, only physical slide rules.
Yeah.
Physical
Can't use a
slide.
tech.
So you can bite the pencil. The the distance is a centimeter.
Do you really have a slide rule out of this?
Yeah,
Interesting.
let me show you.
Slide rule.
That's crazy.
Well, what if my calculator app fails?
You use a slide rule?
Do you have an abacus app too?
Please. say
No,
you have
I
an
mean I know how to
abacus.
count.
Oh, whoops. I'm bad.
Okay,
Yeah,
let's
here we
move
go.
on
Check
to-
this out.
You can slide.
Wow. I didn't even know they made that app.
That doesn't surprise me.
They have an app for everything. Slide
That's
rule
for
even.
that's for like the 60 50-year-old engineers.
I was gonna say my dad has a
a
physical slide rule collection.
Yeah.
It was.
And
it
I
was
think he's
based,
gonna get an iPhone, so now I'm gonna have to tell him about that.
Yeah.
My looking it up was based on a joke I had made around my dad.
Okay,
Of course
so
it
the
exists.
basics of conservation of momentum, and when I was in high school, my teacher taught us momentum as fat mav. I don't know if you guys have ever heard that, but I've never forgotten that. So momentum is equal to a force times a change in time, and then it's also equal to a mass times a velocity. And I just always remember that as fat mav, and it'll be ingrained in my head like that the rest of my life. And so we're conserving that, and we kind of end up utilizing both ideas. P is sometimes often used to symbolize momentum, a capital P, I don't know why, it's just different. So here I've got the momentum is equal to the mass times the velocity, and these are both I's here. Is this a scalar, vector, or tensor?
Scalar.
Vector.
Vector, yep. So there's two I's here with an opposite sides and equal sign. So this is actually three equations. P in one direction is equal to mass times velocity in that direction. P in direction 2 is equal to mass times velocity in direction 2. Mass, which we did last week, mass is equal to the integration over the volume of the density. Right, so all this is putting density in here over the volume, because that's the way we need to think about mass. So now we have a volume integral of the mass times the velocity, or sorry, the density times the velocity that gives us the momentum for that volume in the direction of this velocity. So it's still a three different equations. The mass, it's the whole mass in all three directions. It's just the velocity that's different in the three directions. And then the other way to look at it again is through a force. And here, instead of using F delta T up there, we're looking at it as the derivative of the momentum. The time derivative of the momentum is equal to a force. And our forces, if you did back a few weeks ago, are related to stress. And our traction is like the force vector representation of the stress, right? So the traction vector on a particular plane tells us about the stress involved in that. So if we want to know about the stress, this is where the traction, which is applied to a surface, if we integrate the traction around the surface of our body, that integrates all the way around, and this is like the force we're applying from the outside of the body. And if we integrate that all the way around the surface, then this is the surface integral that contributes to the stress that'll be in there. And so you can look at this as transport of stress across the boundary. So remember, our conservation laws always have a transport term and a production term. And so us pushing on the outside of something with a stress that we can define as a traction on that surface, if we integrate across all of that, this basically helps create the stress, part of the stress that's inside. This is a body force, which is, what's the example we mostly use? Gravity. What are some others? You'll see them with Jeff.
Magnetic.
Magnetics. So you could have a magnetic one. There are some other body forces there, but gravity, of course, is what we mostly use. So this is our production term, because gravity produces stress inside our volume. So our our conservation of stuff is related to transport over the surface times plus production within the body. Same conservation law we've been using. But it's not very useful like this. So what we need to do is turn this into an equation that's actually useful. The concept is all there, but we have to make it useful. The first thing we need to do to make it useful is make them all volume integrals, because that way we can then start to just get rid of those. What do we do to turn this into a volume integral?
Conversion.
Sorry?
ds.
Yeah, so it's the divergence. So it ends up being derivatives of the traction. Well, the traction is redefined as derivatives, and our traction equals sigma ij nj, right? You guys should remember this from your homework. So the divergence of this tells us, if we take this divergence, so here we're summing over the j's but not over the i's. So we still have, because remember this I here tells me that this is going to be a vector. There's still three versions of this equation, dp1 dt, dp2 dt, dp3 dt. So whatever is on this side still has to have a vector, those three components. But with the divergence, we sum over the j's to give us our divergence in that I1 direction. So now we've converted this to a volume integral, and the nice thing is that it's now written in the form of stress, which is what we know more of. Remember, traction really only exists when you define a surface, and if we don't have the surface defined very well, it's hard to use traction itself. So that's why we like stress. So now we have this written as a volume, this written as a volume integral, and this written as a volume integral. We need to do something with this. We have to help so that we can simplify all of this. Because now we've got the total volume integral is just d, this part, dxj, plus our body force. So we can lump those together under one volume integral. We have the derivatives of the stress times plus the body force gives us this integral nicely, but we still have to figure out what to do with this side. So again, this is our volume sigma ij dxj plus our body force. Writing dots on these is really dv. So this is one side of the equation. We can take advantage of, that was the material derivative of the momentum. And so dp by dt is d by dt of v rho vi dv. This was just the definition of momentum, the MAV half of the definition of momentum that I had on the last screen. So if we stick this volume integral in there for momentum, then we're starting to get somewhere, and we can simplify in simplifying this. Taking that derivative, because, does anyone remember what the Reynolds transport theorem is?
I'll let you know on October 23rd.
Actually, this might be the same guy, but you've got the low Reynolds number flow, which is a subtle difference.
Dimensionless, yeah.
Yeah, the dimensionless number. Reynolds transport theorem. Any thoughts?
I had in my notes.
It's where the flow n minus, or the k minus the q nonsense.
I think you're thinking of the divergence theorem.
Oh, maybe that's what I'm thinking of.
So there were, we had the general conservation law, and then we had the divergence theorem, which is what allowed us to take tractions and turn them into derivatives of stresses. And the third important concept that came out of that last week was the Reynolds transport theorem, which we did after we talked about conservation of mass. So it has to do with conservation of stuff.
If V carried by the mass, then we can treat phi the same as we treat the mass.
Exactly. So, if your magic stuff that you want to conserve goes with the mass, then you can treat it like mass, and when we treat it like mass, this derivative and this volume integral are interchangeable. And momentum goes with mass. You can't have momentum without mass. So this clearly fits that rule. So what that means basically is we can put this integral on the outside, and then if we write out our material derivative or Lagrangian derivative into its two terms, we have rho vi dt plus the velocity times rho vi dx. So this, remember, these are the two pieces of acceleration. So this is an actual time rate of change of actual acceleration in time, and this is the apparent acceleration in time because of spatial changes in material. So when all you can see is if you have tunnel vision, what's right in front of you, this looks like a time rate of change of momentum, but really it's because of the spatial change that's outside of your perspective. So just as a reminder of those two key pieces. But now we've got velocity or volume integrals on both sides, which means we can drop all of the volume integrals. So now we can get rid of this volume integral, rid of the dv, rid of the dv, we can get rid of this, we can get rid of this. And then the next thing that we can do really is just taking this a little bit. We can, if we write out all of these to separate the rho and the v in these derivatives, because of the chain rule for product or for product differentiation of products. We get the neat thing about this, and you could write this all out. So we're separating out d rho dt plus v j, d rho dxj. I think this is supposed to be j, I'm sorry. J, because that goes with the j down here. Plus the density times rho vi dt plus vj dvi dxj. That's to equal to that. The nice thing about this now is that this is a version of our conservation of mass. So the mass isn't changing. We can just set this to 0 and get rid of those terms. So
Wait, why? Again?
because we're conserving mass, and the changing.
Oh,
This
right,
is a version of
right,
the conservation
each of those,
of mass,
yeah,
and if
right,
we
I
can't,
see.
if we have to conserve mass, then it has to go to 0. So what we're left with is an actual velocity with time. This is just a simple acceleration. This is that apparent acceleration due to spatial changes. So this is all part of an acceleration of our system. that acceleration, which is in terms of velocities, is related to our stress. Well, it's related to our derivatives of stress, which is what you were getting at with it's the change in the thickness of the water is more important than the total amount of water. So basically this is just force equals mass times acceleration, although if you could write it the other way. So this is what you learned in your high school, your freshman year college class was mass, which is what we're using, density, acceleration, which is that, is equal to force, which is that. So this is conservation of momentum.
I don't understand why you got rid of integration phi dphi, because we still have phi inside. Like before you erase it, I don't know why you.
This integral?
Yeah, like on the top, like yeah, like before.
This was an integral and this was an integral, right? So as long as they're the same integrals,
We just care about the inside.
then the insides have to be equal as well.
Okay.
So once you, if everything is the same integral, then the insides have to always be equal. So we can get rid of that volume integral and it'll still be true, because the insides have to be equal. So basically, yes, conservation of momentum is just the force times equals mass times acceleration that you learned in the old days. Do you guys see that? We've just written it in a different way. And it's just based on the same conservation law. To actually do something useful with this, let's write it all out. Rho plus rho Vj dV dxj equals dots dxj plus xi. So this is now the conservation of momentum in its pretty much its full form. Oh, it is its full form. And again, these are all of our accelerations and these are our stresses. And so when we want to actually solve a problem, though, this is where we need to start making assumptions so that we can take this, so if I say I give you a stress and your body force, how many unknowns are there in this system?
One,
Which one?
the change in time.
Well, so I give you this, you have to tell me what all of the velocities are and what's happening in the system. So
That'd be 4 unknowns, right? The density and then each of the velocity
Yeah,
directions.
the
the
density.
3 velocities and the density. So if I give you the geometry, if I give you then if I give you the geometry and the stress over that whole geometry and the body force and the density,
And there's
and
3.
you can work your way back to the velocity. So, but it's still, that's still a lot of knowns you need that you often don't have. a a lot of unknowns, and we can actually create more unknowns because we're usually more interested in the strain rates instead of just the velocities. Because we want to know how our material is deforming and moving. But so the first assumption that we like to make in this class, that doesn't always apply, but it mostly will apply in this class, is trying to figure out, well, when can we just say that accelerations are 0? It'd be nice just to say, well, things are not moving very much. Yeah, it would be nice if you weren't texting.
No, I'm not texting, but okay.
Okay, whatever you're, unless you're taking notes on your phone.
I did take notes.
Okay, good. That I like. I'm happy with that.
I email myself stuff.
Because if we could say all of this was totally 0, then we can get down to the idea of, well, we're just thinking about a force balance, right? So we just have stresses in a system, and we want to figure out how the system, what the system looks like under that force balance. If it's deforming slowly enough, and then the acceleration still might not be that important. We can still figure out, because we know that stresses relate to strain rates through what relationship? What helps us relate stresses
Is that
to strains or strain rates?
something with tau? No.
So any
Right.
kind of constitutive, so there is a viscosity of some kind or an elasticity, depending on if it's relating it to strain, you might look at an elastic relationship. If you're thinking about viscous fluid flow, then it might be a viscous relationship. But yeah, so and we'll get into better ways of actually writing this out that fits better here than the little springs and dampers that you did. But yeah, that's the idea. But if the first thing we want to do is say, well, what does slow enough mean? Like for this river, can we decide that the river's moving slowly enough that we can throw out all of those acceleration terms?
Well, it's not slow, but the change in velocity. Because I mean, if we say it's slow, it doesn't mean that the acceleration is 0. It's like the change in the velocity. If you meant it by slow, not necessarily the displacement of every point.
Right. Yeah, that's a good point. So you can be moving everything at a certain velocity, but you might still be changing a little bit between those points. So yeah. So there can be a slow change in those, even if the whole thing is moving fast.
Yeah.
The relative change in the velocity might be slow.
Yeah, and the difference between when the flood started and the peak, which you'd imagine there'd be acceleration, or takes a long time. So
it does. So yeah, there are definitely cases where we can assume a river is slowly changing enough. It's one of those that's kind of on the border, depending on the question you're asking. You may or may not be able to throw out these terms. Glaciers, the mantle flows pretty slowly. So those we can usually throw it away. But they've, in the field of fluid dynamics, and there's usually, you can do quite a bit with this, and this comes to what your topic is. We can formalize the way we make that decision by thinking about saying, we can actually say, well, is this, oops, that was eraser. By basically asking, well, what's the magnitude of this term compared to this term and this term and this term? And if we can start to compare what we think are going to be typical magnitudes of each of these terms, then we can say, well, if the magnitude of this term we think is going to be more like 1,000, magnitude of this term is only 1, I'd say, yeah, let's throw it out. So we can formalize that by, and the way it's done is by non-dimensionalizing it is the way you figure out and you derive all of these. And I walk through like how we can take this equation and non-dimensionalize it in here, but that's basically just saying that, for our, I'm not going to go through the entire derivation here. I just want you guys to really understand the concept. So if V is this velocity and it has units of meters per second, big U, V star is our non-dimensional velocity that doesn't have any units. U has units of meters per second, and it's a characteristic velocity for this problem. It kind of is a middle velocity that you might pick. So for this river, we picked, we just threw out numbers, right? We're like, well, based on that graph, 1 meter per second is a base value for the flow, and then it flooded at 3, so I'm gonna say 1 meter per second is a pretty good characteristic velocity. And it's okay if that's not perfect, but you just wanna kind of make your best judgment. So a characteristic velocity, what that does is it allows us to rewrite this term as rho u dv star dt. So we've pulled this u out, and it's now a constant. It's a coefficient in our equation, and it's just a constant value that we pick out. If you do that for all of these, so basically turn all of these pieces into the ones that are inside the derivatives into their non-dimensional form, pull out all of these characteristic values that are the dimensional pieces, then we can divide through, because the dimensions of each term in this equation, like with any equation, the dimensions of all the separate terms have to be equal. And so if we figure out what these coefficients are that hold all of our dimensions for each one of these, and then divide through by one of them, like say we divide through by this one, then basically we've taken this term and given it no dimensions anymore, and the coefficients of all of the other terms now are also non-dimensional coefficients. Does that make sense? It's sort of a little, it's mostly just a mathematical trick, and if we write this all out, well, I'll just jump a little bit ahead, but we can say that dvi star dt I star squared x. Oh, why don't they? I think I've got this typo in here. This is not a squared. I remember this typo before. Equals L rho u squared d sigma ij dxj plus ggi. And for the moment I've left this out here, but you can start collecting these. So right now there's nothing in front of this one, so it's just a non-dimensional term, which means that all the rest of these are also non-dimensional. The way we've divided through. So I've been able to clump with just a little bit of algebra while shifting these things around. I've been able to clump a bunch of these together And so this is a non-dimensional number. The length, the density, and the velocity are characteristic velocities. But we want to take it one step farther because this stress, I still haven't non-dimensionalized the stress in this version of the equation, which is, and stress is a little more challenging to non-dimensionalize, but we can think of stress as you just brought out. In this case, if we have movement, our stress is related to our strain rates, which have some nice dimensions that match up with velocities. So we can, so this has dimensions of 1/seconds, and this has dimensions, it's the viscosity. So rather than non-dimensionalizing the stress as itself, it's easier to non-dimensionalize the strain rates. And if we do that, and a few other things, then this term here ends up looking like eta over rho UL. When I say other things, just moving things around, dividing through by stuff. And this is our non-dimensional version of the strain rate now. But this number now, this coefficient, is non-dimensional, and it kind of has a memory of of these other terms, because it has pieces of these other terms. In this top part, the eta, that's the characteristic viscosity for our system. That's how fluid does the fluid flow. Is it like water, or is it like molasses? Rho UL, the velocity times the distance, some kind of a characteristic distance, and our density. This actually tells us a bit about the momentum from that perspective of movement. And so once you start bringing in velocities and masses, that's when, high velocities are usually where you need to think about accelerations. Not always, because it's more the differences in velocities, but what this relationship is really expressing is how big are the viscous effects compared to the inertial effects. Inertia being like body in motion. Once it's going, it's going to stay in motion, right? So those are our inertial effects, which are related to those accelerations. Like to change an acceleration, you really have to have strong inertial effects in there for these when you have these high velocities. The viscous effects are like the flowing, how the fluid is actually flowing. So if it's a really thick fluid, it's got a high viscosity, then often the viscous effects are going to be much bigger than the inertial effects. So this is like mantle flow. Mantle, really high viscosity, usually moving pretty slowly. The inertial effects are much smaller than the viscous effects. On the reverse, if you are thinking about water in a river, the viscous effects, water is a pretty low viscosity. And so it's pretty easy to get those inertial effects up high enough. So with the characteristic velocity and the characteristic length scale, you can get pretty high inertial effects in water. So this is basically just saying we have these two processes going on. Which one is going to be the dominant process in this question? For this river, it's actually kind of on the edge, but we could stick values in for all of these and decide where we want that boundary to be. It's usually good, the kind of, you could just say, well, if the viscosity is just a little bit more than this rho UL, then we don't want to get rid of it because they're about equal then. It turns out it's a good practice to say that the viscous effects have to be 600 or 700 times more than the bottom to really say that you're getting away from those inertial effects. I think that's the number that you mostly go for. There's a little bit of subjectivity in there. With rivers, you can almost always see it. There's a visual representation. So when do you think, based on your vision of any river, do you think you would definitely have inertial effects going on? What are some features of fast-flowing rivers that complicate flow?
Rapids.
Rapids, right. So turbulence, whenever you start to get into something that's sort of turbulent-y, you don't even have to do this. It's good practice to sit down and go through it, but you know you're going to be in this inertial acceleration thing area. Slow-flowing rivers where it's very smooth, the water is very smoothly moving. That's called laminar flow. Have you guys heard that term? You can sometimes, that's when you really need to check and convince yourself that you either do or don't need those accelerations in there, but generally laminar flow is getting down to where you might be able to get rid of all of these terms. So even though it's moving relatively fast, it's not moving fast enough to overcome, or it's not going fast enough for inertia to dominate the flow over the viscous effects. So this, which actually you write it the other way more often. This is what's called the Reynolds number, and it's just the most common. So inertia over viscosity, viscous effects. It's the most common of these non-dimensional numbers, but you can look at a bunch of other.
U is squared, right?
No, not in this one. Do you have it? There was a square at one point, but then the square ends up dropping out if you walk through the steps. Yeah. So, along with all of the other assumptions that I like you guys to make, this is one of those. Can you get rid of these terms? But this is the first simplifying factor in that system. And if we could do that, then we're down to solving a problem that looks just like this. dxj plus xi, our body forces, equals 0. And that looks like a much simpler problem. And we will dive into examples of solving this equation. And when you do this, we call it low Reynolds number flow, if we decide to get rid of that, if we decide that we can turn it into smaller. If we decide we can get rid of the acceleration terms. So, sorry, I guess kept you guys past it.
There was an experiment how to drop an egg as fast as possible from a building at the University in Haifa. So they rocketed it into the ground, and the egg was in a honey jar. And so.
Using the viscosity of the honey.
Yes. So
nice.
That keeps the Reynolds constant.
Yeah. So even though it's moving quickly, it slowed it down.
On the body force, here one thing, going back even the original just equation for, you have like a volume integral of xi dv. Shouldn't there be like I guess you just know to put like gxi GXI or something. Is
Yeah, yeah.
It just, you have to know,
It's just
the XI is
GI.
always going to be GXI.
XI is
Okay,
just
'cause
the
I
general one.
yeah, because I always treated XI as kind of just being unit vector, or like
It's a big
directions.
capital X is what, yeah, and the way it's written in my notes is it's like a giant X.
Okay.
But
Okay.
then we end up switching and we end up using F for body forces as well, which sometimes is easier
Okay.
than XI. And then just GI, G for the gravity.
Yeah, that was confusing me because then in that equation you had there, I was like, what's the force of gravity?
Sorry about that.
No,
That's in
that's-
here. Sorry.
Question about the equation sheet. So my equation sheet would be relevant for the specific question, not for all topics, or it should have it relevant for all topics.
The equation dictionary is for everything, but how detailed you want it to be is up to you.
Right.
So if you like having, cause that equation.
I have a very specific topic now, so technically I don't need the whole
You
everything.
don't need it for this, but you will need it for your final
And
exam.
I can't add it later, I should add it now. That's what
Yeah.
you're trying to emphasize.
Yes, that's what I'm trying to emphasize,
Okay.
that we want you to add it now.
We see.
You can always modify it later if you decide,
Right.
but we want you to put it in now.